Hello students, I welcome you all to the online video lecture on course Turbomachines. This is the YouTube channel which is named as the Thermal Engineering by Manoj. So in the today's video lecture, we will see the important topic on module number 3 as per your VTU syllabus, Mechanical Engineering 5th semester. Okay. So in module number 3, that is in steam turbines, we have one of the most important topic which is frequently asked in your university level examination, that is the condition for maximum blade efficiency of a 50% reaction turbine or the Parsons turbine. So remember guys, the best example for 50% reaction turbine is a Parsons turbine. Okay. So let us see what are the different assumptions made in the analysis of the derivation. Okay. The first important assumption is the main assumptions involved in the analysis of 50% reaction turbine. The first assumption, the change in enthalpy in the moving blade is equals to the change in enthalpy in the fixed blade, in the row of fixed blade. Okay. So delta HM is equal to delta HS. So delta HM stands for change in enthalpy in the row of moving blades, and delta HS stands for the change in enthalpy in the fixed blades or the starter blades. Okay. Now here, this condition is valid for the 50% reaction turbine. So in module number 2, we have seen that the degree of reaction R is defined as the ratio of enthalpy drop in moving blades to the total enthalpy drop in that stage. Stage in the sense, we have the set of moving blades and the fixed blades. First we have the fixed blades, and after that we have the moving blades. So these two rows together constitutes the first set. We have the fixed blade here. In the next row we have the set of moving blades. These two rows together constitutes a stage. Okay, stage here. This is one stage. Now the enthalpy drop in the fixed blade is represented by delta HS, and the enthalpy drop in the moving blades is represented by delta HM. So the degree of reaction is defined as the ratio of the change in enthalpy or drop in enthalpy in the moving blades to the drop or the total drop in enthalpy in that particular stage. That is the sum of HM, delta HM and delta HS. Okay. So this is the definition of degree of reaction. So if R to be 50% or R to be equals to 0.5, what should be the necessary condition? So the necessary condition is delta HS should be equals to delta HM. Okay. So therefore I can write here delta HM divided by here 2 times delta HM. So both will get cancelled, ultimately value to 0.5 or 50%. This is the first main assumptions made in the analysis of 50% reaction turbine. Let's go to the next. The next important assumption is in the 50% reaction turbine, V1 must be equals to VR2, V2 must be equals to VR1, alpha 1 equals to beta 2, and alpha 2 equals to beta 1. Alpha 2 equals to beta 1. So this is a necessary condition for a 50% reaction turbine. That means the beta 1 and beta 2 stands for the inlet and outlet blade angles of moving blade. Okay, whereas alpha 1 and alpha 2 stands for the alpha 1 is nothing but the angle made by absolute velocity with respect to horizontal, and alpha 2 is nothing but the angle made by absolute velocity at the outlet, that is angle made by V2. Okay, right. Now these are some main assumptions involved in the analysis of the Parsons reaction turbine or 50% reaction turbine. Okay. So for this, let us try to draw the combined inlet and outlet velocity triangle according to this condition. Okay. So this is a common base as it is. common base, that is u here. U stands for the tangential velocity of the runner or the rotor. So this is the velocity, absolute velocity v1, absolute velocity of v1, and it has the two important components, namely horizontal component and vertical component. This is the relative velocity component Vr1. The vertical component of V1 is Vf1, which is known as the axial or the flow velocity component. Let me write here the axial or flow velocity component Vf1, and its horizontal component is Vu1. Its horizontal component is Vu1, that is tangential velocity component at the inlet. V1 is also nothing but the whirl velocity component or the tangential velocity component Vu1 here, right? Okay. Now alpha 1 is the angle made by V1 and beta 1 is angle made by Vr1. This is the inlet velocity triangle. Now the corresponding outlet velocity triangle is this. This will be Vr2. This will be Vr2. And here this is V2. The vertical component is Vf2 and its horizontal component is Vu2. Vu2. So this is alpha 2 and this is beta 2 here. This is beta 2. Okay. So this is a combined inlet and outlet velocity triangle for a 50% reaction turbine. This is not for the scale, but actually when you are drawing the scale and the product, make sure that V1 must be equals to V2, Vr2, V1 must be equals to Vr2, both should be same. Next, Vr1 must be equals to V2. Similarly, beta 1 should be equals to alpha 2 and beta 2 is equals to alpha 1. So make sure that while drawing the combined velocity triangle for 50% reaction turbine, so the velocity triangle should satisfy these assumptions or these conditions. Okay. So alpha 1 equals to beta 2, alpha 2 equals to beta 1, V1 equals to Vr2, and V2 equals to Vr1. So this is the combined velocity triangle for a 50% reaction turbine. Okay. So let us name all these points here. A, B, C, D, E, and F here. Okay. Now let us try to derive the condition for maximum blade efficiency of a 50% reaction turbine, for which first we have to get what is the total work obtained. What is the work obtained from the runner? Okay. So the equation for work done or work obtained per kg of steel is given by U by GC into VU1 plus VU2. VU1 plus VU2. So this is a basic equation for work transfer here. Ultimately, what I want the final expression in the form of the inlet angle. Inlet, the angle alpha 1. Angle alpha 1 is nothing but the angle made by absolute velocity v1. Okay, so this is the angle alpha 1. So ultimately I want the final expression in terms of alpha 1 here, right? So let us continue our derivation here. So we know that the w equals to w by gc, the u by gc into vu1 plus vu2 here. Okay, now how to write the vu1? How to write the vu1 here? VU1 equals to, listen here carefully, the triangle ABD, listen here carefully, in the triangle ABD here, right angle triangle, the cos alpha 1 equals to, the base is VU1 divided by V1 here, okay, the base divided by hypotenuse, or VU1 equals to V1 cos alpha 1. V1 cos alpha 1. So I can write V1 equals to V1 cos alpha 1. V1 equals to V1 cos alpha 1 here. Okay. You can see here. VU1 equals to V1 cos alpha 1. So therefore, I can write VU1 equals to V1 cos alpha 1 here. Similarly, VU2 can also be written as this. VU2 can also be written as, see here, from this triangle DE. DE is nothing but VU2. So how we can write VU2 as, listen it carefully, from the triangle FEC, cos beta 2 can be written as, cos beta 2 can be written as, the base is U plus VU2, total base, divided by hypotenuse is VR2 here, VR2. So ultimately, how I can write VU2 as, just do the cross multiplication, VR2 cos beta 2 minus U, VR2 cos beta 2 minus U. So how I can write VU2 as, VU2 equals to VR2 cos beta 2 minus U, minus U. So let us substitute VU1 and VU2 in this equation. Let us take this as equation number 1, using in equation 1. So I can write W equals to work done per kg of steam, W equals to U by GC as it is, into, instead of this VU1, I can write V1 cos alpha 1 plus, instead of VU2, I can write VR2 cos beta 2 minus U here, into U as it is. Now in the next step, I can write, already we know VR2 is equals to V1 and beta 2 equals to alpha 1. From the assumption for the 50% reaction turbine, we know that VR2 can be written as V1 and beta 2 can be written as alpha 1. So let us use these terms in this equation. So WD, work done per kg of steam, is given by U by GC into V1 cos alpha 1 plus, in place of this VR2, I can write V1 cos alpha 1 minus U as it is, or WD equals to U by GC into 2 times V1 cos alpha 1 minus U as it is. 2 times V1 cos alpha 1 minus U as it is. Okay, I hope this is clear now. Now let us open the bracket by multiplying U here. So WD equals to 1 by GC as it is into 2 times U V1 cos alpha 1 minus U square. Just I have opened the bracket by multiplying the U here. Now for the sake of our convenience, let us divide and multiply by V1 square to the above equation. Let us divide and multiply. Dividing and multiplying the above equation by V1 square, So I can write here WD equals to, so V1 square, just multiply, divided by GC as it is. Now here I am dividing by V1 square here, I am dividing by V1 square. So I can write 2U V1 cos alpha 1 divided by V1 square minus U square by V1 square. Just I have multiplied and I have divided by V1 square. Okay, as we are taking inside the bracket, I have divided the V1 square separately to the each term. Now from the fundamentals, we know that the speed ratio U by V1 is nothing but phi. We know that U by V1 is nothing but phi. Phi is nothing but the speed ratio. Phi is known as the speed ratio. Okay, so V1 and 1 V1 will cancel. U square by V1 square is phi square. So work done per kg of steam is given by V1 square by GC into, So u by v1, 1 v1 is remaining. So 2 times 5 cos alpha 1 minus u square by v1 square is 5 square here. U square by v1 square is 5 square here. Okay. Now this is the work which is obtained from the runner per kg of steam. Per kg of steam. Now let us try to write down what is the energy which is supplied to the runner. What is the energy which is supplied to the runner? So keep it as equation number 2 here. Keep it as equation number 2 because we know that the efficiency, the blade efficiency is given by, it is the ratio of work done per kg of steam by the runner to the energy supplied per kg of steam to the runner. I repeat, blade efficiency is given by work done by the runner per kg of steam divided by the energy or the kinetic energy per kg of steam supplied to the runner. So this is the blade efficiency. So already we got the numerator term, work done per kg of steam. Now let us try to get the equation for energy which is supplied, kinetic energy which is supplied to the runner. Okay. So write down next one. So we got the equation for work done per kg of steam by the runner. Now let us try to get the total energy which is supplied to the runner. Total energy supplied. Total energy supplied per kg of steam to the runner, to the turbine. It is given by the sum of energy supplied to the runner and the energy supplied to the fixed blade. Because in case of impulse turbine, we have seen that VR1 is equals to VR2 in case of impulse turbine. But in case of reaction turbine, VR1 will not be equals to VR2. So please remember, guys, this equation is valid for reaction turbines. Whereas VR1 equals to VR2. This is for impulse turbines. This is for pure impulse turbines. So kindly remember these two important conditions for important turbines, important types of turbines. Okay, fine. Now, how to write the total energy supplied? It is given by the formula V1 square by 2gc plus 1 by 2gc times VR2 square minus VR1 square. VR2 square minus VR1 square here. Okay. Now this term represents the kinetic energy which is supplied to the moving blades, whereas this term stands for the kinetic energy supplied in fixed blade. So the total energy supplied is the sum of kinetic energy per kg of steam to the runner and to the fixed blades. This is the moving blades and this is for fixed blades here, right? Okay. I hope this is clear. Now here I can write. So let us take 1 by 2 GC outside the bracket, 1 by 2, okay, 1 by GC outside the bracket. So what is the remaining term inside the bracket? It is V1 square by 2 plus, let us open the bracket by multiplying 1 by 2 here. So I can write VR2 square by 2 minus VR1 square by 2 here. Now we know that from the assumptions, I can write VR2 equals to VR, VR2 equals to V1. So we can write here 1 by GC times V1 square by 2 plus again V1 square by 2 minus VR1 square by 2. So V1 square by 2, V1 square by 2, that will be only V1 square. So 1 by GC as it is, V1 square minus VR1 square by 2 as it is. VR1 square by 2 as it is. Okay. I hope this is clear. So this is the total enthalpy drop in that stage. This is nothing but the total enthalpy drop per kg of steam, of course. The total enthalpy drop per kg of steam in that rotor, in that stage, sorry, in that stage, total enthalpy drop, or I can say specific enthalpy drop in that particular stage here. Okay. Now, let us apply the cosine rule. Let us apply the cosine rule to this triangle ACD, because what I want the complete final form of equation in terms of strictly alpha 1, because in equation number 2 we have the alpha 1. So let us try to write this equation in terms of alpha 1. Okay, fine. Now here by the triangle ACD, if I apply the cosine rule, VR1 square is equals to U square plus V1 square minus 2U V1 cos alpha 1. This is a cosine rule. Applying cosine rule to the triangle, ACD. So I can write VR1 square equals to U square plus V1 square minus 2 times U V1 cos alpha 1. U V1 cos alpha 1. Okay, so this is the angle. This is the cosine rule for the triangle ACD. AC and D here. Okay, so let us substitute this complete term. In this equation. Okay, in this equation. So what I can write? So here total enthalpy drop per kg of steam is given by, so let us substitute VR1 in this equation. So I can write here V1 square by GC minus, instead of this VR1 square, let us write this complete term 1 by 2 GC into U square plus V1 square minus 2U V1 cos alpha 1. 2U V1 cos alpha 1. Okay. Now in the next step, I can write here. So here just open the bracket by multiplying this 1 by 2 GC here. 1 by 2 GC, just open the bracket by multiplying this complete term. Okay, just open the bracket here. So delta H by kg per kg is equals to V1 square by GC minus, just open the bracket by multiplying 1 by GC here, 1 by 2 GC, U square divided by 2 GC minus into plus minus V1 square by 2 GC, V1 square by 2 GC minus into minus plus 2U V1 cos alpha 1 divided by 2 GC here, right? Now V1 square minus V1 square by 2, we are left with V1 square by 2 here. So I can write V1 square by 2 GC. Just subtract this V1 square minus V1 square by 2 here. So minus U square by 2 GC plus 2 times U V1 cos alpha 1 by 2 GC. Okay. Now let us take the common V1 square by 2 GC here. Let us take the common here. Let us take this term as common here. Outside the bracket. So I can write V1 square by 2 GC as it is into 1. This is minus. So if I take V1 square by 2 GC outside the bracket, so I have to divide this complete term by V1 square by 2 GC. So 2 GC is the same in the denominator, both will get cancelled. So we are left with U square by V1 square. U square by V1 square is nothing but phi or phi square. U by V1 is phi, or U square by V1 square is phi square, plus we are taking 2 by 2GC, denominator common. So here we are left with only V1 square, V1 square, V1 square will get cancelled. So we are left with 2 phi cos alpha 1. 2 phi cos alpha 1. See here, 2 already taken common here, 2 already taken common. So 2 as it is here. Okay. So 5 V1 square, if I divide by V1 square here, V1 will get cancelled. We are left with 1 V1 in the denominator. So U by V1 is 5. So 2 times 5 cos alpha 1 is the remaining term. Now we got the complete equation in terms of alpha 1 here. Okay. So let us take this as equation number 3. Let us take this as equation number 3. Now, what is the definition of blade efficiency? It is the ratio of the work done per kg of steam by the runner divided by the total energy supplied or total enthalpy drop per kg of steam in that particular stage. So this is the definition of the blade efficiency. Okay. So in that blade efficiency equation, just substitute equation number 2 divided by equation number 3. So you will get the efficiency of blade. Now we have both the equations, equation number 2 and equation number 3. So the blade efficiency is given by the formula. Blade efficiency is work done per kg of steam by the runner divided by the kinetic or the total energy supplied. Total energy supplied per kg of steam. Per kg of steam. The total energy supplied per kg of steam here. Okay. So the blade efficiency is given by, so substitute both the terms here, V1 square by GC into 2 phi cos alpha 1 minus phi square divided by this denominator term, equation number 3, V1 square by 2GC into 1 minus phi square plus 2 phi cos alpha 1. 2 phi cos alpha 1. So V1 square will cancel, GC. So we are left with the blade efficiency meter B equals to, take to the numerator 2 into 2 phi cos alpha 1 minus phi square divided by 1 minus phi square plus 2 phi cos alpha 1. 1 minus 2 phi cos alpha 1. Then copy up till here. Now for our convenience, let us add and subtract by 1. Let us add and subtract 1 in the numerator for our convenience. Okay. Adding and subtracting 1 number 1 in numerator of above equation. So meter B equals to 2 times 2 phi cos alpha 1 minus phi square plus 1 minus 1 divided by 1 minus phi square plus 2 phi cos alpha 1 plus 2 phi cos alpha 1 here. Okay. So here I can write meter B equals to 2 times 2 phi cos alpha 1 minus phi square plus 1 as it is, and here just open the bracket by multiplying 2 here with the minus 1. So I can write here, minus 2 times minus 2 times, okay, minus 2 as it is here, divided by 1 minus phi square plus 2 phi cos alpha 1 as it is. 2 phi cos alpha 1 as it is. Let us proceed to the next step here. Let us proceed to the next step. Okay. Now here, let us divide. Let us take the denominator term separately to both the parts. So 2 into 2 phi cos alpha 1 minus phi square plus 1 divided by 1 minus phi square plus 2 phi cos alpha 1 minus, so just divide the 2 divided by the denominator term. Just I am writing it separately to both the terms. 1 minus phi square plus 2 phi cos alpha 1 plus 2 phi cos alpha 1. So both the terms will get cancelled here. Both the terms will get cancelled, the numerator and denominator. So we are left with neta b equals to, neta b equals to 2 divided 2 minus 2 minus 2 divided by 1 minus phi square plus 2 phi cos alpha 1. 2 phi cos alpha 1. Sorry. So this is our equation for blade efficiency. So let us rub this. Let's proceed to the next step. So we got the blade efficiency as, is it okay if I write here? Fine. So the blade efficiency, just now we got blade efficiency equals to 2 minus 2 by 1 minus phi square plus 2 phi plus 2 phi plus 2 phi cos alpha 1 plus 2 phi cos alpha 1. Okay. I want the condition for maximum blade efficiency. I want the condition for maximum blade efficiency. For that, I have to differentiate this equation with respect to phi and equate it to 0. As we have seen in the previous derivations, like blade efficiency, the condition for maximum blade efficiency of a single stage impulse turbine and two stage impulse turbine, etc. So we have done the same steps here also. Let us differentiate this complete term with respect to phi and equating it to 0. So the differentiation with respect to phi of this complete term, the term which is in the denominator, 1 minus phi square plus 2 phi cos alpha 1 with 0, adequating it to 0 with respect to phi. So the differentiation of 1, 0. So here we'll get minus 2 phi, and here the differentiation of 2 phi cos alpha 1, 2 cos alpha 1 is a constant term. So plus 2 cos alpha 1 remains as it is, which is of course equals to 0. So therefore phi equals to cos alpha 1. Phi equals to cos alpha 1. So this is the condition for maximum blade efficiency of a 50% reaction turbine. Phi should be equals to cos alpha 1. Okay. Now let us substitute this condition in the blade efficiency equation to get the maximum blade efficiency, the equation for maximum blade efficiency. So I can write using I think this is the equation number 4. This, let us keep it as equation number 4. Using the above condition, in equation 4, in equation number 4. So I can write the maximum blade efficiency equals to 2 minus 2 divided by, so 1 minus phi square is there, so cos square alpha 1 plus 2 times phi. Phi is again cos alpha 1, cos alpha 1, cos alpha 1, cos square alpha 1, 2 cos square alpha 1, 2 cos square alpha 1 here. So the maximum blade efficiency is 2 minus 2 divided by 1 plus cos square alpha 1. See, 2 cos square alpha 1 minus cos square alpha 1 is cos square alpha 1. So take this term as LCM. So I can write 2 times 1 plus cos square alpha 1 minus 2 as it is divided by, so is taking this term as LCM, 1 plus cos square alpha 1. Okay, so simplify this above equation. So I can write 2 plus 2 cos square alpha 1 minus 2 divided by 1 plus cos square alpha 1. So plus 2 minus 2 will get cancelled. So we are left with the maximum blade efficiency equals to. So we are left with the final form of equation, that is the maximum blade efficiency for the 50% reaction turbine. Maximum blade efficiency for the 50% reaction turbine as 2 cos square alpha 1, 2 cos square alpha 1 divided by 1 plus cos square alpha 1. So this is the final form of equation for the efficiency. So with this we have completed the derivation part of 50% reaction turbine, which is most frequently asked question in examination. So if you have any doubts anywhere, so watch this video repeatedly, and further if you have any doubts, you can put your comments or the queries in the comment box, or else you can message me on my WhatsApp number 988-6539-074. This is the WhatsApp number. So if you have any queries, any doubts regarding the turbo machines models or any of the model here in turbo machine course, you can contact me personally, and you can definitely I'll try my level best to solve those queries. Okay, so don't forget to like the channel, share the channel, and subscribe the channel. So thanks for watching this video completely. Thank you and have a great day.